In this video, we're going to look at another type of problem that we may solve using dynamic programming. It is called the resource allocation problem. The main characteristic of the problem is that we have limited amount of resources that we must allocate among several activities. For example, in this problem, we have $6,000 to invest, and if we invest $DJ in investment J, then we will get the return, which is the function of RJDJ, and the functions are shown like this. So let's say you spend D1 in investment 1, then the return equals 7D1 plus 2. And then there's a restriction saying that the amount placed in each investment must be the multiple of 1,000. And then we would like to maximize the return in the net present value obtained from the investment. How should we allocate the $6,000? And then we can't use linear programming to solve this problem because the return is not proportional to the input. For example, for investment 1, if you invest $1,000, then the return equals 9. But if you invest $2,000, the return equals 16. Instead of 18, it is just 16. That's why this is not proportional, and then we can't solve this using linear programming. So the stage for this problem is the investment 1, 2, 3. How do we know about this? Well, we always try to choose the stage such that when one stage remains, the problem becomes easy to solve. For example, if you only have one type of investment, let's say investment 3 is the only option, then it's very easy, right? All the money that you have, just put them all in investment 3 because that's the only one possible investment. Now, if you have 2 investments, then it becomes a little bit harder. If you have 3, it becomes more confusing, and even more 4, 5, and so on becomes more and more difficult to solve. From that idea, you know that the stage is the investment. Is a good choice to become the stage is the investment, because if only one investment available, then the problem becomes easy to solve. So in this case, we have 3 stages, stage 1, 2, and 3. So same as before, I will ask you the similar question. What is the possible amount of money that we still have when we face investment 3? The correct answer would be 0, 1, 2, 3, 4, 5, and $6,000. Well, these are all possible because, for example, we may have spent all our money on investment 1 and 2. Right? We don't know yet whether that is an optimal decision, but that is a possibility. So we need to consider that. It means that now, because we have spent everything on investment 1 and 2, we only have 0 money left when we face investment 3. That's a possibility. On the other extreme, we have spent nothing on investment 1 and 2. So we still have $6,000 intact with us when we face investment 3. So these are all the possibilities. Now for each of this amount of money that we still have when we face investment 3, we may say that let's say if you still have $4,000 left with you, because this is the very last investment that you may invest, then your decision would be investing those all $4,000 in investment 3. Again, because this is the last investment that you may invest, so why would you like to keep the money? Just invest them. At least you will get some return, right? So if you still have $4,000, then you invest those $4,000, and then the return would be 4 times 4 plus 5, so $21. And here it says X34 is the decision at stage 3, when you begin this stage with $4,000 on your hand, would be investing those $4,000 to investment 3. Okay, so you see that all these decisions, they are all exactly equal the state in this case. because whatever money that is left on your hand, you just invest it to investment 3, because again, this is the very last investment that you may choose. Okay, so these are the states from 0, 1, 2, 3, 4, 5, 6, and these are the decisions corresponding to each of the state. Let's move backward to investment 2. So we are now at stage 2. Same question, what is the possible amount of money that we still have when we face investment 2? The answer is again the same from 0, 1, 2, 3, 4, 5, 6. So let's say if we have $0 left, so the state is 0. The only possible decision is 0 because you don't have money, so you cannot invest anything. The return is 0. The return from the later stages is also 0. This is F3 0. So the total NPV from investment 2 and 3 is 0. 2 and 3 is 0. Best return is $0. Best decision is also $0 if stage equals 2 and state equals 0. This is not very exciting, right? Let's see another example. Now, what if when we face investment 2, we still have $6,000 on hand? So the state is 6, and then we have a lot of possible decisions. Starts from invest nothing at investment 2 up to invest everything in investment 2. And this is the return for this stage. For example, if you invest nothing, the return is nothing. If you invest $6,000, then the return is 3 times 6 plus 7, which is 25. And let's say another example, if you invest 4, then the return is 19 because 3 times 4 equals 12 plus 7 equals 19. So that's the return from investment 2. Do not forget to add the return from the later stages, in this case F3 something. And that something is the amount of money that you have when you begin or when you face investment 3. So for example, if you start investment 2 with $6,000, you invest nothing in investment 2, you will start investment 3 with $6,000. So this 29 is F36. This is F35, F34, F33, F32, F31 up to F30. Take the sum and then pick the maximum among this. So the best return is $35,000. The best decision is investing $1,000 if the stage equals 2 and the state equals 6. As usual, I strongly suggest you to do the calculation at least for one of the states until you reach the conclusion and you are also able to interpret the conclusion. So let's move backward again until we reach stage 1. Same question, what is the possible amount of money that we still have when we face investment 1? The answer is $6,000 and only 6. Because we know from the problem that at the beginning of this problem, we have $6,000 on hand. And investment 1 is the first investment that we face. So obviously we still have those $6,000 on hand. So the state is $6,000 and we have this many possible decisions. For each of these decisions, you calculate the return for the investment 1. For example, if I spent $1,000, the return would be 7 times 1 plus 2 equals 9. Do not forget to add the return from the later stages, which means plus F2 something. The something is the state at the beginning of stage 2. So the state equals 6 minus x1 because we begin stage 1 with $6,000 and then we invest as many as $1,000. So the one that the amount of money that we still have when we begin investment 2 equals 6 minus x1. And then take the sum, and based on all these total return from investment 1 to 3, we pick the one that is the maximum. So the maximum is the best return, and then the best decision at stage 1 equals investing $4. So this is the best return and best decision corresponding to stage 1 and the state 6. So this table may be written in terms of equation that looks like this. Among all possible decisions xt, we take the maximum, which is we try to maximize the return by investing xt dollars in investment t plus ft plus 1 d minus xt. Okay, so d is the money that we have when we face investment t, and then we spend xt. So the remaining money that we have for the next investment equals d minus xt. Now to read the optimal solution, we go to stage 1. Here we see that we need to invest $4,000. So from this row and also this conclusion, we need to invest $4,000, and then we'll begin stage 2 with $2,000 remaining. At stage 2, we look at the one that has the state of $2,000 remaining, and then the best decision here is investing $1,000. So we will begin stage 3 with $1,000 remaining. So at stage 3, we look at this row, $1,000 remaining, and then the decision is just invest those $1,000. Okay, so that was the optimal investment plan. Invest $4,000 in investment 1, $1,000 in investment 2, and $1,000 in investment 3. If we follow that plan, then we will get the maximal return of $49,000, as you can see here. Okay, so that's the end of this video, how we solve the resource allocation problem using dynamic programming. In the next video, we're going to look at another problem, which is called knapsack problem. So see you on the next one. Thank you.